Okay, so hello everyone, and welcome to our number 3 seminar. Today, we have the great pleasure to have Sebastian Bartling from the State University. He's going to talk about closed p-adic fields and Rapoport-Zink spaces. Thank you very much.
Yeah, thanks a lot for the invitation to speak here. And yeah, okay, I'm sorry about the technical setup, but so I want to about a project that is still a bit in progress together with Andreas Mihac. And the aim of our project is to prove the arithmetic fundamental in function field case. And since this is like our main motivation for our project, I want to start by recalling for you what the arithmetic fundamental lemma says. Okay, so it's an identity between two sides. One is usually called the analytic side, the other the geometric side. So I want to start by stating the analytic side. For this, I fix a prime p, which will be fixed throughout the talk. Q is some power of p. F is a local non-Archimedean field. OF is the ring of integers. Pi is going to be a fixed uniformizer, and I want that the residue field has Q elements. So F could either be of characteristic P when it's like FQ Laurent series in the uniformizer pi, or it's a finite extension of QP. So we also fix E over F, the quadratic unramified extension. We're going to denote by sigma, the non-trivial element in Galois. And then by local class field theory, I get a character from F star to Z modulo 2Z. And then so the analytic side of the IFL, it's in the end some kind of combinatorial expression, and which is like phrased in terms of twisted orbital integrals. And to explain these orbital integrals, we look at the inclusion of GLN minus 1F into GLNE, where I take a matrix and put it into the upper left corner, and I put a 1 in the lower right corner. Then I can look at what people usually call symmetric space um, in this literature. So S and F. So these are elements in GLNE gamma, which have the property that gamma times sigma of gamma is the identity. And well, on the space, now GLN minus 1F acts by conjugation. And so recall that we call an element in GLNE regular semi-simple if these vectors that I wrote down there are linearly independent. So that's a very explicit way to say it. Uh, like the abstract way to think about it is that the stabilizer is trivial and the orbit is Zariski closed. And okay, so let's take a regular semi-simple element in SNF. Then I'm going to look at the following derivative of a twisted orbital integral. So now, okay, let's first look at what this orbital integral is. I take a Haar measure on GLN minus 1F, which I normalize such that on GLN minus 1OF, it has volume 1. Then I can take the indicator function of SNOF, and then I run over the orbit of gamma under conjugation. And then, okay, I also twist this integral by, okay, I can apply this character that I had upstairs from by class field theory. I can apply it to the determinant. And then, okay, I also want to introduce some dependence on a variable s, which is a complex number. So I take the absolute value of the determinant to the s. Okay, so this is some integral, and so this assumption, regular semi-simple, it buys you that this is actually converging. And now you can look at the derivative along S. and you can evaluate this derivative at 0. Okay, so that's one side of this arithmetic fundamental lemma. And one can be very, very explicit what this actually is. It's like, can write down it's a certain count of lattices in vector spaces associated to the setup. But for the rest of the talk, it's not really that important. Um, yeah, what precisely this count is. So that's one side. And the other side is something that just a priori looks completely different and has nothing to do with the before. So this is what people call the geometric side. And that's actually going to be the main focus of my talk. So on the geometric side, we're going to look at certain intersection numbers for arithmetic intersection problems. And this intersection will be taking place on what we call Rapoport-Zink or Hartrell-Feynman spaces. These are, so I want to be in a unitary situation. And for now, you can think of Rapoport-Zink spaces or Hartrell-Feynman spaces as kind of local analogons of Shimura varieties or Stuka spaces. I'm going to define later precisely what Rapoport-Zink spaces are and what Hartrell-Feynman spaces are. So this is a reasonably well-behaved formal scheme. And we will see it's actually defined in terms of a deformation space. So part of the data you need to fix to construct it is like what you deform. And the thing you deform will buy you, in particular, an n-dimensional Hermitian space for this quadratic extension. So I can use this to construct a unitary group, which by the setup will have the form, it's a unitary group of a Hermitian matrix J, which has the form diagonal J1, 1, and the J1 can actually be chosen to be actually of this form. So this will correspond to kind of the non-split Hermitian space for this quadratic extension. And okay, when I say it's a unitary Rapoport-Zink space or Hartrell-Feynman space, in particular, what is very important is that I have an action of this big p-adic group, this unitary group on my formal scheme. And this action I will use to define a certain cycle that I want to then intersect in a certain way. So let's take a priori an element, just any element in this unitary group. Then we can define a cycle sitting in middle dimension as follows. So okay, we have all these moduli problems n, and one can check that they are embedded into each other. So we have a closed embedding of n minus 1 into n. This will, to construct this one, will use the universal object over n1. And well, this is by what I said before, it's just a formal spectrum of OF brief. And well, if you have this embedding, you can look at the graph, which sits in this fiber product. And then if I have the graph, so this is kind of, it's a closed formal subscheme of this fiber product here. And then because I know that my group UFN acts, I can translate the cycle using this element. Okay, so what this tells you is like starting from an element in UFN, you can construct a certain cycle. And we want to use this cycle to define the arithmetic intersection problem. So for this, we still need to say like a link between the previous side that I stated here, the analytic side, and the geometric side. And for this, one uses what is called a matching relation. So we say an element in the symmetric space matches an element in the unitary group if so both lie in GLNE, and I can require that they are conjugate by an element in GLN minus 1E. So that's what we mean by two elements in the symmetric space and in the unitary group match. Okay, so now I roughly introduce these two sites, and so we can state the arithmetic fundamental lemma conjecture, which is due to Wei Zhang, and it says the following. So if a regular semi-simple element in the symmetric space matches an element G in the unitary group of Vn, which is also regular semi-simple, then we have the following identity. So on the one side, we have this value of the derivative of the orbital integral that I introduced in the beginning. And on the other side, we have basically the intersection number of the graph of this embedding here together with the cycle that I constructed using this element G. So technically, it's the Euler-Poincaré characteristic of this perfect complex. Okay, and here I wrote down a definition of what this is. Okay, but yeah, this is the arithmetic intersection number, the right-hand side, and on the left-hand side, we have this combinatorial expression, which is related to a certain lattice count. And okay, the claim is that these two things are equal. Are there any questions about the statement of this conjecture? Okay, if this is not the case, then let's see what is known about it. So the status is that for p not equal to 2, it's completely solved in the p-adic situation. So whenever you have whenever you're in a characteristic 0, then by work of Wei Zhang, Miat Zhang, and Siju Zhang, this is completely solved. And so, but it's still open in the function field situation. And a reason why their proof does not directly carry over to function field is that so what they do is like they globalize the situation to Shimura varieties and then use certain modularity properties for generating functions for certain cycles on Shimura varieties. But then, so you prove some equality for global numbers, where on one side you have some intersection number, on one side also some analytic expression. But once you have this global identity, you want to go back to the local identity that you're interested in. And there they need that they work over a geometric object where you have like residue fields of different characteristics. I mean, in the end, you use something like if you take the logarithm of different prime numbers, then they are Q-linearly independent. And the different prime numbers will come from like different residue characteristic of the Shimura variety. And well, obviously, in a function field, you cannot do this because all residue fields will have the same characteristic. So at least naively, it's maybe not so clear how to adapt their proof. So what we will do in the project is somehow deduce the function field case from the p-adic case. And that's where these closed p-adic fields come in, which we'll tackle. And I mean, the main point of my talk will be more talking about like what are the geometric objects that will power this reduction to the p-adic case. Okay, but let's first roughly tell you the idea of like how we prove the arithmetic fundamental in the function field situation. So there's something called the philosophy of closed p-adic fields, which, okay, I don't know too well where this started, but people usually attribute it to Krasner already. Deligne used it, Kashtan also, and very recently also Daniel Hurta. And so what is this philosophy saying is that the theory of p-adic fields approaches the theory of equal characteristic non-Archimedean fields if you make the ramification index grow further and further. Um, this is That's what people understand by this philosophy of closed p-adic fields. So technically, how we implement this, how this is implemented, is as follows: like for every natural number, you choose a p-adic field, so a finite extension fi of qp with ring of integers oi, fixed uniformizer pi I. Sorry, and I always want that the residue field is identified with fq. So I have this family of p-adic fields. They all have the same residue field, but what is critical is that I want that the ramification index of fi is greater or equal than I. So for I goes to infinity, the ramification should also go to infinity. And for I equal to infinity, I will take a local non-Archimedean field of characteristic P. So it's the Laurent series field over FQ in the variable pi infinity. Okay, yeah, that's what I put at infinity. And now by the structure of these ramified extensions, I know that I can fix an identification between OI modulo pi I to the EI, which is just you mod out P, and then can fix an identification with on the other side O infinity and you mod out pi infinity to the EI. Yeah, I mean, basically what you use here is that you can realize OI somewhere as you have the bit vectors of FQ, and then you have a polynomial ring, and you mod out something that is Eisenstein at P. And okay, that's how you get this identification. And we want to have it so that pi I is mapped to pi infinity, and it's the identity on FQ. Okay, so here I really use this the structure of how these things look like. And so when I have the setup, the idea is to put the two quantities that I had in the arithmetic fundamental lemma. I want to put it into a function depending on this I. Um, and then we want to show that these two functions are constant around infinity. So, I mean, it should be like if you plug in an I, you get like this twisted orbital integral derivative for an element gamma I, which sits like in the symmetric space for the field Fi. And here in Gi should be the intersection problem on the Rapoport-Zink or Hartle, unitary Rapoport-Zink or Hartle-Feynman space for this field Fi. And so the idea is to put this into functions and show it's constant around infinity. And then if you have this constancy, you can deduce, you can deduce the equality at infinity by knowing it for i's which are close to infinity. Yeah, you know it in the p-adic situation, and this way you can deduce it for the equal characteristic situation. So that's roughly the idea. And then, of course, the whole the big question is like, how are you able to how are you able to construct these functions? And so I don't want to talk about this analytic side, um, but the main work is really to construct this function on the geometric side. And this is also like these, yeah, what I want to tell you is like how to set these Rapoport-Zink spaces into a family indexed by I to construct this function. Okay, that's the very rough idea of how to do this. Is there a question about this?
Excuse me. So do you also construct these fields Fi, or you're saying that for any
So what we do is like
you fix a family and then
whenever
show it?
when you take a p-adic field, if you take a characteristic P local non-Archimedean field, it will have this form.
Mhm.
And then you choose a family of p-adic fields having these properties.
But this is not unique, right? But you're
No, no,
saying
no,
that
there are many.
for any family, this
Exactly,
strategy works,
exactly.
and you don't want to change the family. I'm saying that someone gives you the family, and then you can run the argument, right?
Right. I mean, the family is in the end for what we want to do not important. Which one specifically you can take? You
Mhm.
take.
I
Right.
see. Okay. Yeah. Thank
So the idea is really you start from the characteristic P situation, and then you give yourself any family
you.
that right. Because for any family for these p-adic things, we already know the arithmetic fundamental amount. So
Okay.
you don't have to be specific about the choice you take.
But I mean, I don't know exactly how the fundamental arithmetic fundamental lemma works in p-adic field, but so you don't need some compatibility between them, just equality of two functions, right? Two quantities are equal for each
Yeah.
field,
I
and you want
don't
to take a limit. Okay.
don't need any a priori any compatibility between the FIs, if
Okay.
this was this. Yeah.
Thank you.
Yeah, I mean this situation maybe somehow also shows up in tilting, right? Or where you typically want maybe they are included in each other. I mean, you look at something like the uh you join p roots of unity or something like this, and yeah. But okay, here we can take like whatever family we want, which yeah. Okay, are there more questions?
No, thank you.
Okay, great. So okay, that's what we want to do, and so what I want to explain now is like how could you go about constructing this function I goes to int gi? Remember, int gi was like this intersection number, and okay, for this I want to construct what I call profinite families of Rapoport-Zink spaces. And then for this, let me recall what Rapoport-Zink spaces are. So they parameterize certain p-divisible groups with extra structure. So let me take k over qp a finite extension. Then as the test category, I take nilp OK. So these are OK schemes such that, and pi is a uniformizer in OK. such that pi is theoretically locally nilpotent on S. And then the category BTOKS is defined as follows. So you take a p-divisible group over S, and here I also recalled you the definition of a p-divisible group. So it's a certain FPP, so it's a abelian sheaf on the big FPPF side of S, such that the multiplication with P is an epimorphism. That's where the divisibility comes in. And we want its like P infinity torsion. So the colimit of the P to the n torsions is isomorphic to X. And I want that the P torsion is representable by a finite locally free group scheme. Typically, how these things arise is like if you have an abelian scheme over S, then you take the colimit of the P to the n torsion. That's one. Okay, and then we want to endow this with extra endomorphisms. So take a ring homomorphism from OK to the endomorphisms of X. And this should be what people call a strict OK action. So I have the Lie algebra of X, or you can also take the co-Lie module if you wish. This is a quasi-coherent OS module. So I have an OK action also there. So now I have two OK actions on this Lie algebra. And so one by like scalar multiplication and the other by like these extra endomorphisms. And the requirement is that the two things agree. Okay, so sometimes people call this also strict OK modules. And so this is the p-adic situation. And for the function field situation, the correct analogon of BTOK was defined by Rapoport-Zink. So let's take, oh, and that's a typo, sorry. OK is this power series ring. And K is the Laurent series field, sorry. Okay, anyway, so let's put ourselves in the characteristic P situation. Then we have the following definition due to Hartle and Zink. So here, the test objects will be FQ power series Z schemes S, such that Z is theoretically locally nilpotent on S. And then BT power series FQZS is the category of FQZ modules on the big FPPF sides of S, such that the following properties hold. So the first is that we want that Z is an epimorphism. Then we also have like this Z infinity torsion property. And we also want that all the Z to the n torsion parts are representable by finite locally free group schemes. But we also have to, and this is different from the situation before, just for p-divisible groups, we also want to put a condition. It's like a bit like the strictness condition. It's kind of the finite locally free group scheme analogon of the strictness condition that I had before. And the requirement again is like that somehow FQ acts by scalar multiplication on certain differential data associated to this finite locally free group scheme. For Q equal to P, this just means that the P-Verschiebung of this finite locally free group scheme is zero. But I think in general, yeah, you have to, it's slightly technical. Like it's a notion that was introduced by Faltings. And basically what you require is, so you can take the co-Lie complex of this finite locally free group scheme, and you require the existence of a certain cochain complex, which gives rise to this co-Lie complex in the derived category. And you want that on this cochain complex, you have also an FQ action, and this FQ action should be by scalar multiplication. Okay, that's what this is. And then, okay, this is so a requirement on how the FQ acts. And then we also want that Z acts by scalar multiplication on the co-Lie module. And then, okay, I think I never defined this. Okay, so that's the inverse limit of the Z to the N torsion, like the co-Lie module of the Z to the N torsion. And well, this is just the pullback along the unit section of the Kähler differentials, the finite local free group scheme. Okay, so that's the definition that Hartle and Zink give. And actually, they define something more general, what I define here. But we don't need this more general notion. Like for expert, this is somehow related to the fact that for these Stuka spaces, we can also bound the singularity by non-minuscule co-characters. So there are also kind of non-minuscule versions, these BTs, but we don't need this here. Okay. Other questions about this definition? Okay. So, I mean, it sort of looks very similar to the p-adic definition, modulo like that we have to have this more subtle strictness condition here on the finite locally free group schemes. I mean, one can also say that if you have some BTOK, then you can look at the pi to the n torsion and you can prove that it's also strict as an OK module in the sense of faultings. Yeah. So in this sense, it's really pretty analogous. Okay. Very good. So these are the objects we want to parameterize in the modular problem. And so now let's define the modular problems. And these are these Rapoport-Zink or Hartle-Riemann spaces. So for this, I fix a math BBX in BTOK of K, where K over FQ is algebraically closed. And then I send S in this category nil OK to triples where X iota is a BTOK and rho is an OK linear quasi-isogeny defined on the mod pi reduction of my scheme. Okay, so maybe I should say something about quasi-isogenies.
Just before that, sorry. And, OK is now in characteristic P, or it can be either.
It can be both.
Can be both here. Okay, so
That's
little
why I
k
defined.
is little k is the residue. What is little k and what is capital K? So you said that k is over
Okay.
FQ
Yeah.
algebraic closed field. So this is the residue
Should I
field of
call it
OK.
F? Yeah, so O big K, where K is like the local non-Archimedean field, and little k is an algebraically closed extension
Okay,
of the
nothing.
residue field.
Okay, thank you.
Yeah, okay, that's not the best notation. Yeah,
I think it's
maybe
clear
big
that
K.
it's capital K. Yeah, I think it's clear now. Thank you. Just wanted to make sure.
But yeah, I mean, I tried to put the notation here so that I can state it uniformly in the p-adic case and the function field case. So yeah. Okay, so quasi. I think in the end there will be a definition of a quasi-isogeny. It's kind of it's a word like a morphism, sort of an isomorphism that's only defined after inverting pi. And yeah, I mean, it has better technical properties. For example, for quasi-isogenies, you have unique lifting along nilpotent thickenings, for example. But I think yeah, later there will be a definition. Okay, so this is our modular problem, and so by results of Rapoport-Zink from the 90s, and so together with Manuel Hoff, we have reproven it last year. And so this like the p-adic situation, and then by results of Hartle-Fiemann in 2008, this modular problem is representable by a nice form scheme. Actually, like Hartle-Fiemann and also Rapoport-Zink, they prove more general statements. Hartle-Fiemann really way more general, and Rapoport-Zink you allow more structure on the X. But at least in the book of Rapoport and Zink, this is like the key backbone, or like the key technical result that gets the construction of the modular problems going. Okay. And okay, so now I have like these modular problems that are defined both in the p-adic situation and in the function field situation. And so now what I want to do is I go back to this fixer family from before, or as before. So I have Fi, Oi, pi I, they all have the residue field Fq. And at infinity, I have like this Laurent series field over Fq. And I require that the ramification index is greater or equal than I. And I also fix this identification gamma I. The idea is now, so I have all these modular problems. I'm OI, and I want to put them into a family, yeah, to one family together. And the base over which this will be done, so this ring was already introduced by Lee Hurter. He wrote a paper where he showed that like the Fark-Schulze geometrization of local Langmans is also compatible with this idea of this philosophy of closed p-adic fields. And in particular, he already introduced the ring that we also needed. So let's define this. So for n greater or equal than 1, I define On. So these are sequences x1, x2 until x infinity in OI mod pi I to the n, which are in a certain sense eventually constant. So what this means technically is that there exists a bound greater or equal than n such that for all indices that come after, under this identification gamma I that I introduced, the value at I is the same as the value at infinity. Okay, and so this makes, here's for example where we sort of need that the ramification index grows to infinity because so I want to vary the d, so the d can be very, very big. And then but if I say like gamma I here, I want that this makes sense. But for this, I need that my ramification index at I is greater or equal than n. Does that make sense? Because I mean, I also want the n to grow. The n should grow, and then, but this gamma I is bar is only defined when ei is greater or equal than n. So that's why I also need the ramification to grow to infinity for I goes to infinity. Mm. Okay, so that's like a very, very, it's like a certainly pretty big ring, but it's still manageably big. And what we do now is So these rings ON, they assemble into an inverse system, and then one can take the inverse limit. So that's a subring of this product, the product OI with O infinity. And so that's the p-adically complete ring, where pi is now the product, or like pi is like pi1, pi2, until pi infinity. And it has the property that, so if we mod out pi, then what we look at is eventually constant sequences in FQ, right? Like if I put n equal to 1 here, I want that, and I mean, all residue fields are identified anyways, and the gamma I are the identity on FQ. So what I'm writing down here is they exist about D such that for all I greater than this, they all become the same. So a fancy way to say this, and is like we look at locally constant functions from the one-point compactification of n to fq. Well, and these are just eventually constant sequences in fq. And then what this implies in particular is that the underlying topological space of the formal spectrum of O is isomorphic to this profinite space, which is the one-point compactification of n. Okay, so that's going to be the base over which we want to put the Rapoport-Zink spaces into the family. Is there a question about this definition?
And do they say something about the structure of this ring
Mm.
other than this periodically complete?
Yeah, okay, so what we always use in the argument in the structure is that so mod pi, it looks like this, or mod pi to the n. We know it's On. And this ring On, it's what is called coherent. It's a coherent ring, for example. That means all finitely generated ideals are also finitely presented. Um, like it's a filtered colimit along flat transition maps of Noetherian rings. So although it's not Noetherian, it still has some nice finiteness properties built into
See.
it. And this is in the end critical for some of the results that we're going to prove.
Okay. Okay,
And
thank you.
beyond this, okay, I don't know. And that's what we use all the time. Like that these ONs are coherent.
Okay, thank you.
Okay, so that's the ring O, and now we want to define like the family version of these BTs. So I can look at now nilp O. So these are O schemes such that pi is seriously locally nilpotent. And we define the following category, BTOS. So these are O modules on the big FPPF side of S. And well, we require the following. So the first two axioms are these usual BT axioms. So I want that pi is an epimorphism and X is the colimit of the pi to the n torsion. But now I want that what we call if we have a fiberwise action. So the requirement is the following. So I have this ring homomorphism from O to the endomorphisms of X. What I can do is if I have my S over O, I can restrict it to a fiber, right? I mean, this ring O has uh, has a surjection due to OI. So I can look at the fiber product, and I can also pull back this sheaf, and then I can also pull back endomorphisms to the fiber. And what we require is that this action that I get then on the fiber factors over the evaluation map at I. So I have this X lives over S, and S lives over O, and then I can always go to a fiber like for in N union infinity, and so if I restrict my O action to this fiber, I want that it's just OI acting there. Okay. Yeah, so one can require this, but now I have uh, I'm in a situation, so I have this gamma I, the OI action on the fiber, and I can just require that XI gamma I is a BTOI. Okay, well, that's the definition of the objects we want to parameterize in our modular problem. Okay, so uh, then
Sorry, there's something confusing. So you had ON and you OI. So these are different things, right?
oh, that's again that notation. Oh, sorry. Uh,
Right. So
yeah,
so
yeah,
this
yeah, yeah.
OI is really
That's the ring of
the ex
integers in the p-adic field Fi.
uh,
Um, yeah, sorry. The O(n) is really that's O mod pi to the n. Hmm.
okay. But the OI there is not ON. Is not the ON when N is
No,
I.
that's
Okay.
not O(n).
Okay,
Yeah,
so
yeah, sorry.
uh-huh. Okay.
I don't want that. I mean, I don't
Yeah.
require that p to the I is zero. I
Yeah,
require
yeah.
that the action factors over the evaluation at the fiber I.
Yeah, okay.
Oh man, that's very bad notation. Hmm. No. Okay, is that clear now?
Yes, yes, yes. Okay. Thank you.
No, sorry. Um, okay, so that's our key definition, and now we gonna write down again the modular problem. So for this, we fix math BBX, so it's in BTO, and now we look at so K, little k is still an algebraically closed extension of FQ. And now we can look at locally constant functions from the one-point compactification of n to k. So in other words, eventually constant sequences in little k. And um, so I require that at all fibers, the OI height is the same and the dimension is the same. So the absolute height will go to infinity, but I want that the OI height is the same everywhere. So that's the framing object. And so part of our paper is also concerned with actually explaining that this exists. You know? So, I mean, you can make this definition, and it could also be that uh, if you're really in a situation where S lives over O and it's not just concentrated in one fiber, you have to explain that the things you write down there actually exist. Um, so we do this for these profinite families of perfect fields by developing some version of the Udini theory over this ring O. So Lee Hurta in his paper, he already defined Witt vectors over this ring O. And then one can define Dieudonné modules for these width vectors. And okay, one can prove a classification result uh, for BTO of these profinite families of perfect fields. And then to define this Dieudonné module, that's really just a matrix with entries in these ovid vectors. And this you can write down. So this way you can at least show that these things for these profinite families of perfect fields exist. We also have a version of Lubin-Tate theory. So that's uh, another way to say that these things exist. Okay, so but now we can fix this. And then we define the notion of isogeny. Isogeny is an epimorphism such that the kernel is finite locally free. And here's the definition of a quasi-isogeny. So it's a global section of the Hom sheaf, but I invert pi. And locally, I want that I find a number such that pi to the n times rho is an isogeny. And then we also prove something like the unique lifting lemma in this situation. And okay, so and now I can state our first result. So we show that this functor take S and it sends to equivalence classes X in BTO over S and rho a quasi-isogeny defined on the mod pi reduction. That this thing is representable by a formal scheme which is adic of finite ideal type and what we call locally formally a finite presentation over O and formally smooth. So, okay, explain here what this means. So these adjectives are there because we're like in this non-Eutherian situation. And then, yeah, you have to put, I mean, you have to prove the correct finiteness properties still in this situation. And the correct finiteness properties is the following, like locally we want that our formal scheme is spiff A, where A is an I-adically complete ring and I is finitely generated. So this is this finite ideal type. And then this formally of finite presentation means the following. So, I mean, A is a continuous O algebra. So some power of pi lies in I, and I want that these maps O mod pi to the m times k goes to I mod I, A mod I to k. These are finite presentation. Um, okay. So that's and formally smooth is really just formally smooth in the sense of lifting along nilpotent quadratic, like square zero secant. Okay, so that's the result we have about this modular problem. And then I still have 4 minutes, right? Uh, okay. So I still have to, I mean, I want to have this function int gi, right? Um, so I have, so we, using this MO, we also define a unitary version of this. And we also define the correct analogons of these cycles that I defined in the beginning when I talked about the arithmetic fundamental lemma. And now these cycles, you can always restrict to a fiber and intersect there. And that's going to be our function. Okay, so you have like this formal scheme defined over this big ring O. You have cycles in this big formal scheme, but what you can do is now for every I, you restrict the whole situation to a fiber and then take the intersection number there. Mm. And then we prove this technical lemma, which shows that in this finitely presented situation, these fiber-wise intersection numbers are really constant around infinity. Uh, okay, so I mean, lemma means so like if M is like adic, a finite ideal type, and locally a finite presentation, and you have a perfect complex such that all the cohomology groups are supported on a closed form subscheme, which is actually a proper finitely presented scheme over O, then I can look at the function. I take I and send it to the Euler-Poincare characteristic of K restricted to the fiber I, and we show this is constant around infinity. Um, okay, and then now I have something about the proofs, but maybe this is when there are more questions. I mean, that's gonna be a bit technical. I don't know. Or should I? Uh, I don't know.
Well, I mean, thank you very
Maybe
much.
that's already enough information.
I mean, I'd like to know if you used somehow the geometry of these Rapoport-Zink spaces to prove this. I mean, maybe some way,
um, this lemma,
yeah.
yeah, we use. Okay, so I can here I say something about proofs. So I mean, this representability result is once you have enough theory for these BTOs, with a little bit of work, you can rerun the arguments of Rapoport-Zink. That's how we do this here. But for this lemma 2, to get this constancy around infinity, the idea is so if you have this perfect complex, then you first oh, finitely presented A mod J modules. So A mod J is a local piece in this proper scheme over which on which this thingy is supported, and then you actually just use how this ring O looks like. Mm. I mean, you use that
Okay.
the mod pi to the m reduction is this colimit where above D, the fibers don't move anymore. And then if you finitely present it over such a colimit like this, it will descend to a finite stage of the colimit. So that's what I write down here. And then if you take fibers above D, then you can see they're all identified. And it's because these sequences we required in this definition of the ring O that these sequences are eventually constant. So the answer is I use the geometry of these formal schemes, which have this finiteness property, but it's really a general statement about formal schemes having these properties. It's not specific to a modular problem of BTOs.
Okay. Thank you very much. Uh, are there questions?
So I have one question. So may I ask it?
Mm-hmm.
Sure.
Yeah. Okay. Actually, in this, I mean, where you compute the Euler characteristic there in last lemma. So I'm just wondering, arguments like algebraizability, I mean, local algebraizability of these Rapoport-Zink spaces. Okay, which is like, I mean, one requires strong conditions, of course, but is that kind of things are of any use in proving that or simplifies anything?
Mm. So these local algebraization statements um, they use the uniformization, right? By some kind of Shimura variety.
Right. I mean, one requires something. I mean, the p-divisible group like coming from a global one or the local distributor
Exactly.
comes from a global. I mean, that kind of things. I mean,
I think we don't
I
have
mean,
access to statements like this here
mhm.
because I don't know what should uniformize our Rapoport-Zink space over the ring O. Um, yeah.
I see. Hmm.
Because
Hmm.
you
Okay.
would
So,
uniformize it by some global object which sees abelian varieties and Stuka, but then I have no idea what like the global analogon of BTO would be. So that's why we can't use this.
Okay, maybe one, recourse to, make use of the moduli of global G Stukas and then the uniformization theory over there. And
Right,
then
but this
one
is
has,
just in
one
the
can come with that kind of arguments about this local algebraic up to some sort of étale quotient, let's say.
right, but this is
Yeah,
only in characteristic P, right? It's
right, yeah.
just
Hmm. Hmm.
um,
But the analog also, one could say something like, the Farg argument for, Shimura varieties and then Rapoport-Zink space over there. So there is a difference, of course, because here one has to pass to some sort of étale quotient, but then one would not require that. Yeah.
okay, so maybe no, sorry, I didn't really understand. I mean, so my worry is more that I don't know whether there are any uniformization statements uh, for this Rapoport-Zink space that we define. Because I don't know what would uniformize it. Because it would be a global object that sees at the same time like the p-adic situation and then also the characteristic P situation. But I don't, I mean, basically, I don't know what would be a global version of BTO. That's, yeah. Does it make sense as an
Well,
answer? I don't know.
well,
Um,
yeah. Let's see. I write an email about it to you, so maybe later.
great.
But okay, I see. Okay, thank you very much. By the way, this Hartel-Freeman Rapoport-Zink
Mhm,
space for general G was like
mhm,
constructed as part of my thesis.
mhm.
Yeah. I see. Mhm.
But you use probably you use the Stuka perspective, right? Like for any G, you
Right.
have like
Yeah.
Stuka perspective. So actually, something that I was when I was writing this paper, um, I was not sure I can like for the representability in the function field case of this MOK uh,
Mhm.
was not 100% clear to me what are the Stuka that correspond to this BTFQ power series that I defined here. I tried to look
Mhm.
a bit to the paper of Hartle and Zink, but um, in any case, the argument that we write down also works uniformly in both situations.
Yeah. Yeah. But I think in our paper there is a remark explaining this
Ah,
in my paper with Urs. So, yeah.
so
But
you
I
you
have
say
also
what
to remind myself.
okay. Yeah, this
Yeah.
would be, I mean, I would be interested in to know exactly what are the local Stuka that
Mhm.
correspond to this category BT that I defined here. Um,
I mean,
Mhm.
I also have a preprint, which which is very similar to Hartle Singh's paper, but
mhm.
I like the exposition in my paper better. I can send it to you. I don't think if it's available online, so I can send it to you maybe. I
Yeah,
mean, this is
that would be nice.
my perspective is more in the spirit of Rapoport Sync. So
Mhm.
anyway, so I
Also,
also have some questions. Yeah,
maybe you
if there.
already wrote the argument that we gotta use. Yeah. Mhm.
So
Um,
first of all, I wanted to know if the fibers of these Rapoport Sync spaces you have. So these are Rapoport Sync spaces for some framing physical groups, right?
mhm.
So can I go the other way around? So can I just have write any physical group that I have as a fiber
Mhm.
of this? So you mentioned some existence result that this the fiber is not empty. So I
Yeah,
want to know
right,
if I
right.
can always
Put it into a family. Yeah.
yeah.
in general, the answer is I don't know. But in this unitary situation, the answer is yes. At least for right there, we prove it. We prove like if you have like this unitary object um, for the fiber at infinity, you can always lift it to a family. Um, this is just like in this situation, up to isogeny, there's just one. And
Hmm.
then whenever you write down something over O and you go to the fiber, you will hit it. Um, but in
So good.
general, I didn't, I also didn't think about it too carefully when one can, like for general, like for like general groups, when one can lift uh, something in a fiber to something to a family overall. Yeah.
This is looks like a very cool device that you have here because I mean, of course, you use it in one direction to get the result AFL for the function field case, but I think one can use it for many different purposes, right? So
Yeah, hopefully.
uh,
I
yeah,
don't. I
so
mean,
this is very cool.
I should say we also have a work in progress together with Katsuhiro, where we use the same idea to affine Grassmannians. So we have this width vector affine Grassmannians, and then so in these width vector affine Grassmannians, so these are perfect in schemes. You have these Schubert varieties, and what we show, and in general, like the Schubert variety in the width vector version is not just the perfection of the corresponding Schubert variety in the power series version, but what we prove is there is a bound on the ramification such that if you work with ramified with vectors for fields which are more ramified than this bound, then this is true. Then like the Schubert variety and the width vector affine Grassmannian is really just the perfection of the corresponding Schubert variety on the power series side. So in particular, you get some kind of finite type models after
Hmm.
passing to this. But I also there, I don't know any. I mean, I keep on asking people, do you know an application of this result? And I, yeah, I don't have a very nice application yet for this.
Which one?
This local constancy of Schubert varieties.
Ah, okay.
Mm. And typically, so here we use it to show something in the function field case, given that we already know it in the p-adic situation. But there are not so many statements like this, right? Usually things are more easier to be shown in the function field situation, and then afterwards you have the p-adic situation. So it would be really nice if you can also have the flow the other way using this construction, but I didn't see any example yet of this. But
Uh, I wouldn't worry. I think it will show up at some point. But how about GS structure and these things?
yeah,
So can one do also this?
so yeah, when I was also defining like displays, like O displays, um, and O GNU displays, one can define all this. So the point is a bit what I'm a bit unsure about in this situation is if you define these displays over O, it's not clear if you have test up. I mean, you always want to construct these things in a way that if you work in with a test object which lives over a certain fiber, you get back the old notion. Okay.
Hmm.
Now let's say we have a test object which just lives over the infinite fiber, then I'm not sure we get back local Stuka. The point is, if you take the ramified width, that's kind of funny actually. If you take the ramified width vectors for the power series ring, then if R is not perfect, I don't think this is the power series ring for R.
Mhm.
So
Mhm.
for perfect test objects, this display theory gives you at the infinite fiber still the local Stuka theory. But for non-perfect things, this is something slightly different. So it could be that this is just a defect of the width vector construction. Maybe if there's some kind of prismatic construction
Yeah,
for width
that's what I was thinking about.
over O, you actually get power series. But I mean, yeah, one can think about probably, and I didn't think about this yet. But yeah, that's all I can tell you in this situation.
Okay,
Mm.
very nice. Thank you very much. Are there other questions?